Good morning, everyone, and welcome to this session on prioritizing technical debt as if time and money matters. So this is a broad topic, so I want to jump right in and have a look at the challenges that we all face when building software systems. I like to think that these challenges they are very well captured in something known as Lehman's laws of software evolution. And today I want to present two of the most important laws to you here and see if they resonate with your experience. So the first law of software evolution is the law of continuing change. And this is where Lehman claims that the software system has to continuously adapt and evolve, or it will become progressively less useful over time. Is this something you recognize? Yeah, I see a lot of people nodding. That's right. This is the very reason why we are never done. A successful product is never done, right? We need to add new features to it. We need to respond to market needs and competitors, right? So software will continuously evolve. What I want you to do now is to look at the second law of software evolution. And this is the law of increasing complexity. Because when our system evolves, its complexity will increase unless we actively try to reduce it. Do you notice the tension between these two laws? On one hand, we have to continuously adapt and evolve our code, but when we do that, its complexity will increase. And this can very easily lead to a vicious circle. And the main problem with that vicious circle is that what we tend to see are symptoms, not the real root cause. And to make it even more challenging, we're going to see different symptoms depending on who we are, depending on what our role is. So if we are technical leaders, what we tend to see is an impact on our product's roadmap. We notice longer and longer cycle times, longer delivery times, right? So it simply takes longer to get new stuff out. As a consequence of that, we tend to lose predictability. I mean, software estimation is already something like a black art, right? And with growing technical depth, growing complexity, it's going to be even harder to guess when something will be done. What we tend to notice as part of the development team is something different. We tend to notice that our job becomes pretty stressful. It's demotivating to work with code of increasing complexity. No one really wants to do that. And very, very often, we end up with things like key personnel dependencies. You know, that big subsystem over here that only one person knows how it works, and that person is on vacation. Finally, what our users tend to experience is this. Bugs, right? So it's an impact on the external quality of our code. And the real root causes tend to remain largely hidden, opaque, and obscure. And the main problem with technical debt to me is that it's so important, but it lacks visibility. You know, there's no way we can take a software system, pull it out, turn it around, and inspect it for technical debt, right? We just cannot do that. So the big question is, how can we bring visibility to technical debt? There have been several attempts at that. And one of them that's relatively common is to try to quantify technical debt. And I've seen this happen a number of times. And the way this works is typically that you have some tool that's capable of scanning the source code. And that tool has a number of rules. So it scans your code, and each time it finds a violation, it kind of records that as technical debt. And then it has some heuristics to put costs on it, right? So the first time I saw that done at scale was maybe 6 years ago. I did some work for a client to help them prioritize their technical debt. And shortly before my arrival, that client had done something very interesting. They had taken one of these tools and thrown it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. 4,000 years of technical debt. You know, let me put that into perspective for you. 4,000 years ago, that was here. That's the start of recorded history through the invention of writing. So, you know, when I tell that story, I always start to think, what kind of programming language did I use, right? Most likely a Lisp or a Fortran, something like that, yeah. But anyway, 4,000 years of technical debt, the fun thing is that it might actually be accurate, because a lot of that debt grew in parallel by having hundreds of developers work on the code base, right? But how useful is it? Is it actionable? Where do you start? Is all debt equally important? There's just no way of knowing. So my conclusion after seeing this attempted a number of times is that quantifying technical debt might be an interesting exercise. It's almost always depressing, but it's not actionable. More specifically, and I think this is one of the most important things, is that technical debt just cannot be prioritized or identified in the source code. And I'm going to talk much more about that soon. But still, remember Lehman's laws, continuing change, right? Increasing complexity. It's very clear that we have a trade-off between improving existing code versus adding new features that the business calls for. So it is important to prioritize tech debt, right? But how do we do it? This is a question I've been spending 10 years thinking about, and the approach I'm using is something I call behavioral code analysis. So a behavioral code analysis is different from the way we typically talk about code analysis. Because in the behavioral code analysis, the source code itself, it is important. It really is, right? We need to distinguish good from bad and stuff like that. But it's even more important to understand how we, as a development organization, have interacted with the system we're building. So in a behavioral code analysis, the emphasis is on people. People like us, people who build code. And to do a behavioral code analysis, we need to get some kind of behavioral data of software developers. How do we interact with the code we're building? How can we get that behavioral data? Well, the good news are that you all already have that. We're just not used to think about it that way. Because I'm talking about our version control systems. And if any one of you have read any of my books or seen my previous talks, you kind of know that I'm a big fan of version control. So I guess that's another one of my odd hobbies. But the reason I'm fascinated by version control is because version control is really behavioral data. It explains how we have interacted with the code, who did what, when did we do it, how frequently, stuff like that. So let's embrace version control data, and let's try to make all of this specific by looking at a case study of a real-world code base. And for this case study, where I would like to show you how you can prioritize technical debt amongst million lines of code, I like to pick a code base that I think all of you might be familiar with. It's a code base that I think some of you actually carry around in your pocket as I speak. I'm talking about this. I'm talking about Android. So this part of Android, it's something known as the platform framework base. It's 3 million lines of code, most of it written in Java, and it's developed by thousands of developers. So let me start here by walking you through this visualization so that you know what you see. This is something I call a hotspot visualization. And the first thing you need to know is that if you have a look at the screen and you see those large circles, the ones that blink right now, each one of those corresponds to a top-level folder in that code base. So it's a hierarchical visualization that follows the structure of your code. So if this was your code base, you would recognize the names of those large circles as important subsystems or high-level components, right? It's also an interactive view, so I can click on any one of those folders and I can zoom in to the level of detail that I'm interested in. And once I get to the lowest level of detail, I see that each file with source code is visualized as a circle as well. And you see that those circles, not only do they have different size, they also have different colors. So let's have a look at the dimensions. The first dimension is the size dimension, which is used to express something called code complexity. Basically, how hard is this code for a human to understand, right? So the larger the circle, the more code, the more challenging. But let me tell you this about code complexity, because this is actually the least important dimension we're talking about technical debt. Because complexity kind of has this property that it's only really a problem when and if we need to deal with it. So maybe we have this overly complicated piece of code, we haven't touched it in 5 years. I mean, it's not perfect, right? But is it really a problem? So we need to figure out, does this complexity actually have an impact on us? And this is data that we can pull out of our version control system. So we can go to version control and look at how frequently do we need to work with that particular module. So we measure a number of commits, things like that, and we sum them up, and we use color to represent it. And when we combine these two dimensions, we can identify hotspots, which are complicated code that we have to work with often. Now, I'm going to return to Android and this specific hotspot, but before I do that, I'd like to take a detour into the territory of code complexity. Is there such a thing as code quality? Is it something you can actually measure? Well, I'm a little bit skeptical, and the reason I'm skeptical is because I personally try to avoid the word code quality. And the reason I try to avoid it is because it kind of suggests an absolute, whereas reality is much more complicated. And I've taken a lot of inspiration from a research paper, the one that I'm quoting here. You can look it up in the slides afterwards in more detail. But what this paper tells us is basically that software complexity is so multifaceted that we are doomed if we look for a single number to capture that concept, right? So instead, I took a lot of inspiration from the second paragraph here that tells us that the most promising approach is simply to identify specific attributes of code complexity, and then we measure these attributes separately. Then we can kind of capture all these dimensions. So I've been doing a lot of work on that over the past years. I have a write-up if you want to read more details. Oh, you cannot see it because it's hidden behind the subtitles. Great. But you can see it on the slides. You should all have access to them. Anyway, I choose to call it code health. How healthy is your code, rather than going down that quality route. And the way I do it is basically that depending on language, I might sample 20, 25 different factors that are known from research to correlate with increased maintenance costs, increased risk for defects. And I'm going to show you some examples. And then I kind of aggregate those metrics, I normalize them, and I can kind of categorize every single module into healthy code, unhealthy code, and anything in between. Before I show you how that looks, just to give you an example of what kind of issues do I look for. I look for the things that we know has a real impact, right? So it's a little bit of a higher scope. So one example is low cohesion. So you find a module, and low cohesion simply means that that module has way too many responsibilities. It does many different things. And code like that, not only is it going to be hard to understand, it also tends to become a bottleneck, a coordination bottleneck for different teams, right? Because everyone ends up modifying that code. I look at different patterns in code complexity. One thing I tend to emphasize is what I call deeply nested logic. So we've all seen that code, right? It's when you have if statements inside other if statements. And the reason I put emphasis on that is because there's some very, very good research that suggests that roughly 20% of all programming mistakes are due to things like deeply nested logic, right? It's also easy to avoid. And then, of course, things like brain methods. You know, brain methods, these overly large, complicated functions that kind of centers the behavior of a class or module, right? So anytime you need to change something, you have to go into the brain method. So things like that. So I sample them, and I normalize and I categorize. And I can then visualize a different view of software system. I can visualize how healthy is each piece of code here. And you can see here that the red areas, those are the parts of the code with low code health. Now, when we have this, which can kind of serve like a quality view, we have the hotspots that kind of show the people behavior. If we combine these two, then we are finally capable of prioritizing technical debt. And I want to show you a different example. This is another code base that I think a lot of you might be using. This is Kubernetes. And the first thing you see is how we identify code that has low health, code with quality issues. So those are all those red areas. However, when we add the hotspot view, we can immediately see that most of that code is not really our concern, right? Because it's stable. What the hotspots do is that they send a positive message that tells us that, yeah, we don't really have to fix all that technical debt. We have to fix the technical debt that has an impact on us, that has a high interest. So we get a very clear starting point here. Now, let's dig a little bit deeper. Let's return to Android. So the number one hotspot in Android is a module called ActivityManager Service. Isn't that a wonderful name, by the way? Right? You have activity, which might be something from the problem domain. But then you have two words, manager and service, and each one of those in isolation kind of signals a unit with incredibly low cohesion. Now you combine them, and you combine it with the fact that this module has 20,000 lines of code, right? And there have been 74 developers working on it over the past 3 months. I know that from version control. So hands up, who would like to refactor this piece of code? No one. That's very good, because we should never ever take on a refactoring at that scale. We need to make it actionable. So what I do when I find these gigantic hotspots is that I use a technique I call the X-ray. So I take that module, I parse it into separate functions, right? And then I look at the Git log, where do each commit hit over time, and I sum it up, and I get hotspots at the function level. And this is what I use to select a specific starting point for each refactoring. Let's look at Android and see what we can find in ActivityManager Service. So the number one hotspot at the function level right now is a function called handle message. And we see from the data here that handle message has been modified 98 times just over the past year. So like twice a week, some developer is impacted by excess complexity of handle message. And how complicated is handle message? Well, we can get an ID in the final column, the one that says cyclomatic complexity. So cyclomatic complexity is one of those really, really rough complexity metrics. It's basically calculates the number of logical paths through that function, right? So each time you have an if statement plus 1, a loop plus 1, and so on, right? And what I find useful with cyclomatic complexity is that it's also a pretty good estimate on how many unit tests you need to cover just that function. So for handle message, you would need 108 unit tests. And I guess that says something about the complexity, right? We see that it's also a fairly large function, 500 lines of code. So 500, that's a lot for a single function, isn't it? It is. But 500 lines of code is much, much less than 20,000 lines of code, which was total file. And it's definitely less than 3 million lines of code, which was total system. So more important, we are now at the level where we can act upon this information and do a focused refactoring based on how we, as an organization, have worked with the code. So to wrap up my part here on hotspots, I would like to explain a little bit more about why hotspots work so well to prioritize technical debt. And please look carefully now, because what you might see here might be one of the most important slides I'm going to show you today. So you have 3 graphs at the top. Each one of them shows the same kind of data. On the x-axis, you have each file in the system. And those files are sorted according to the change frequency. That is, how many commits, how many changes have you done to that code. And the number of changes is what you see on the y-axis. Now, if you look at those 3 systems, you see it's 3 completely different code bases, developed by different organizations, different teams, right? Targeting different domains, different lifetime spans, different programming languages. Everything is different. And yet, they all show exactly the same pattern. They show a power law distribution. And this is something I found in every single code base that I ever analyzed. And I probably analyzed around 300 code bases by now. So this seems to be the way software evolves. And you know what? This is actually very good for us. Because what it means is that in our code base, it's very likely that most of our code is going to be in the long tail, which means it's code that's rarely, if ever, touched. And that's the part of the code base where you can actually live fairly safely with a certain degree of technical debt, because it's a low interest on that debt. On the other hand, we see that the hotspots, they only make up a minor part of the code base. But that part of the code, that's where it's vital. That's where it's important to keep technical debt at a minimum to really, really maintain healthy code. because any code quality issues in a hotspot will quickly become really, really expensive because we work on that code so much. Now, with that covered, I like to extend technical debt to the people side because it's impossible to talk about technical debt without mentioning people. And the reason I say this is because getting the organizational side, getting the people side of code wrong has killed more projects than even Visual Basic, right? So this is important. And I like to kind of approach this from the perspective of legacy code, which is related to technical debt, but not the same thing. So what is legacy code? Well, legacy code to me is code that somehow lacks in quality, right? Typically has low code health. And the key point, it's code that we didn't write ourselves. That's legacy code. And the second point, it kind of occurred to me a number of years ago how important that one is. So let me tell you what happened. I went to work for a large organization. I did a workshop for them, right, where we analyzed hotspot in their code and we discussed potential refactorings improvements. And that team, we've been spending a day doing that, and they had 2 code bases. And both of those code bases look fairly good. Sure, they had some technical debt, but nothing critical, right? It's something that you could manage. But then towards the end of the day, someone told me that, you know what? We actually have a 3rd code base as well. So I thought, okay, interesting. Let's run a hotspot analysis on that one too. And everyone kind of start to give each other strange looks, and then they turn to me and say, yeah, but we don't really have to do that because we know that 3rd code base, it's going to be a mess, right? So I said, that's even more interesting. Now we kind of need to bring it up. And we did. We did an analysis of it. And guess what? That 3rd code base was exactly as good as the other 2. There was virtually no objective difference, right? Same numbers, same level of code health. And at first, people really couldn't believe that, right? So we had to dig deeper and even start to, compare code and that kind of stuff. But then it occurred to me that the reason that 3rd code base was considered to be a mess was that it had a very different history. Because that 3rd code base had been originally developed in a different part of the organization, located in a different country. That team had since been disbanded, and the new team had kind of inherited that code base. So the reason they found it a mess was simply due to unfamiliarity, right? Both with the problem and with the domain. And when I learned about that, I started to think, this is really fascinating. Can we create legacy code that quickly? So let's do a case study and consider how quickly can we take a current code base that we understand and turn it into legacy code. What do we have to do? And for this case study, I'm going to turn to a different code base. I'm going to use an American code base, ASP.NET MVC Core from Microsoft, which is a framework for building dynamic web applications. It's a little bit of a smaller code base, roughly like 300, 400,000 lines of code, 180 contributors. And this is what the hotspot analysis looks like. Now, the interesting thing, if you remember when I talked about power loss and hotspots, is that when you look at the evolution of software, power loss, like in nature, are everywhere. So if we instead look at the number of, you have 180 developers in that code base, right? But if you look at the contributions, you will see that again, it forms a power law curve where most of the code is written by a small group of people. And again, this is an open source project, but it's something I've seen virtually every closed source project as well. It seems to be the way software evolves. So for our purposes, what's the risk if one of those core contributors leaves? What's going to happen? Well, we can actually measure that impact. And to do that, we need to figure out some kind of, ownership stuff, like who wrote what, which we all know is really, really easy because we are in version control wonderland. So if we look at Git knows exactly which developer that wrote which piece of code, so we can fetch that information, we can aggregate that into teams and stuff like that. And we can generate a knowledge map. So it's the same visualization style as I used for hotspots, only now the colors are different. So blue means that this is code written by the current team. So this is where we can expect to have active knowledge inside the organization. The different shades of gray are code written by former contributors. So this might be people that have already left the company or are working on some other project, right? And what we can do now is that we can identify one of those core contributors and we can see what's the impact if that person leaves. So I did that. So I looked up one developer that I happen to know works at Microsoft full-time at this code base, and I start to see what happens if this person leaves. And I visualize that for you here to the right. So the areas indicated with red is the simulated knowledge loss if just one person out of those 180 leaves. The question now is, if this was our project, should we be worried? Yes, we should, right? Because we're losing knowledge of like 1/3 of the code base. It's going to be a disaster. So what can we do if this is a real world scenario? What I have found successful is to use this in combination with the hotspot measure. And I specifically look for 3 different properties. So first of all, if I have a module that I know that we're going to lose knowledge of that module, and then I also know that it's relevant because it's a hotspot, meaning it's likely we'll continue to work on that code, then it's relevant. And if the impact is high, meaning we have a high complexity, low code health, then I know that I have a real issue. So what I would do in this case is most likely I would pair that developer up with someone else on the team, and I would have them refactor the most critical hotspots together to mitigate a potential offboarding risk. And the main reason I showed you this offboarding case study is because I really want to make my point that there is so much more to code complexity than just code. And in particular, social factors are going to influence how we perceive a code base. And yes, we do tend to overestimate the complexity of unfamiliar code. Now, before taking some questions, maybe you would like to try this on your own code. So let me point out the tools I'm using. And we have to remember that this is a fairly young field, which means that when I start to work on this kind of analysis, like maybe 10 years ago, there weren't any tools available that could do the kind of analysis I needed. So I developed a tool that I call CodeMath. I've open sourced it, so it's available on my GitHub page, and it's completely free, of course. So if you're interested in getting started, that could be a starting point. It's a simple command line tool. What I've been working on over the past 5 years is the next generation of that tooling, which is called CodeSyn. So CodeSyn is available at codesyn.io. There's a free community edition if you want to check it out. And finally, what I find so fascinating is that we can get really far with just Git. So just to give you some example, I think this has to be my favorite Git command. Did you know that if you type git log with the -l flag, then you can specify a function name inside a file, and you can have Git trace the evolution of that function. So that basically gives us something like a simple version of an X-ray analysis directly from our command line. Now, I've come to the end of my talk, and I really just want to point out that a behavior code analysis is something I found very valuable for my own career. It's something I'm using almost on a daily basis. But I also like to point out that a behavior code analysis technique like hotspots doesn't really replace anything, except maybe heated arguments and wild speculations and guesses. Rather, I view these techniques as a complement to your existing expertise, to your existing knowledge, right? Because a hotspot analysis can help you focus your attention to where it's likely to be needed the most. And software development at scale is always going to be a challenge, so I do think that we need all the support we can get. And if you're interested in diving deeper into this field, I have my new book, Software Design X-Rays, that covers hotspots and lots of other behavior code analysis techniques. There are also a number of open source examples at codesyn.io. There's a showcase tab that you can click on and you can explore hotspots in well-known open source projects. I blog regularly on these topics at codesyn.com and my private blog, adamtornhill.com. And before I take questions, let me use this opportunity to say thanks a lot, everyone, for showing up to my session, and may the code be with you. Thank you.